All right, this is going to be a long video, and it's going to be a lot of notes. So grab your snacks and be ready for this one. Be ready to pause often so you can write stuff down, and be ready to watch some videos. I linked a lot of MythBusters videos in here. They're not required to watch at all. They are just there as partially just entertainment. They're brain breaks, especially for people in person. They don't have anything else to do in class, so we got to get some brain breaks in there. But they also do help a little bit understand, like, what are we even talking about in this case. And so they're real life examples of some of these forces we're going to talk about today. Today we're moving into our new unit, forces, and one of the main things we have to talk about are free body diagrams. Before I even get there, I want to stress this about free body diagrams. Last unit we did T-charts. They were just a tool to help us accomplish the task better. They were not necessary to do, but I instructed you guys to do them because they helped organize your work because there was so much going on. Free body diagrams are similar. They're just a tool, so don't think of them like actual physics. They're just a tool to help us understand the physics and be able to notate them down better. That being said, free body diagrams will be required. So you do need to take really good notes on them today because they're part of physics, like etiquette, part of the curriculum. You have to know exactly how to do free body diagrams, and you have to do them precisely. So we're going to talk about forces. A force simply is a push or a pull. This is the best way to describe it. Anything that pushes or pulls is a force. It's a vector quantity. So we're going to have a magnitude and we're going to have a direction to every force. Forces are going to cause masses to accelerate. And so last couple units we've been talking about position, velocity, and acceleration. But not all things accelerate. If we want something to accelerate, we have to apply a force. Forces are going to be measured in newtons. We're going to write it as just a capital N whenever we abbreviate it. And there's many types. They're often given two categories. I don't know if we'll actually have any test questions over this, but I wanted to go ahead and throw this in there because it's in the TEKS. We're going to have contact forces, which are forces that like physically touch each other. So like friction, you have a box on a slope, or like if you have a couch on a carpet or whatever, there's a lot of friction when you try to push that couch. So it's contact force because that couch is physically touching the surface. It's called a contact force because they're in direct contact. This is different than a field force, like a magnet. A magnet, they don't have to be directly touching each other to be attracted to each other. They have these magnetic fields around them that you can't see that attract each other. But there's a bunch of field forces too. There's electric field, there's magnetic fields, there's gravitational fields. There's other field forces out there. There are a bunch of forces we got to talk about in specific, though, okay? And that's why the notes are kind of heavy today, and this is why you're going to need to pause a lot. The first one is called the force of gravity, also known as, like, everyday language, is weight. If you talk about your weight, you are talking about the force that gravity is pulling on you. It has a special equation, the force of gravity, or weight. So you might also see it as W, but we're going to use F of G because we're going to try to keep all the forces as F. The force of gravity is equal to mg. M is a mass. You should recognize this already. And then G is 9.8. It's the same number we've been using for G, 9.8. And so if you want to find the force of gravity on an object, all you have to do is multiply 9.8 times your mass. So if you have an object that is 80 kilograms. If you want the force of gravity, you're going to do 80 times 9.8, and you're putting in a calculator. 80 times 9.8, and you get 784 newtons. Realize that even though we're talking about weight, even though we're talking about the force of gravity, we're using a different unit than you're used to in your everyday language. You're used to pounds. We're going to use newtons. There is a conversion between the two. If you want to, you can Google the conversion in case you're curious. It doesn't matter. We're going to be using newtons in here, but pounds is another unit of force. You also need to know the difference between weight and mass. They're kind of thrown around. If you go to the doctor in another country and you say, hey, what's my weight? They're going to tell you, or they say, hey, your weight is like 80 kilograms or something. They're going to tell you your mass, actually, even though you ask for weights. They throw it around as if they're the same thing. They're not the same thing. There's an important distinction Mass is the measure of the amount of matter in an object. It's a measure of amount of stuff in an object. Mass is how much stuff there is, while weight is the force of gravity on the object. And so we have this relationship between the two, that the weight is equal to the mass times g, but obviously that means they're not the same thing. You get a different number. And the real easy way to differentiate them is think about, if you take a car to the moon, you're not changing the mass at all, right? The mass stays the same. It has the same amount of matter in that car, whether it's on the Earth or on the moon. But of course, the weight is different. When you go to the moon, you weigh less. When you go to the moon, that car is going to weigh less. And so the weight changes because the force of gravity changes, but the mass stays the same. And you can see a picture. Of course, our force of gravity is always going to pull objects down towards the Earth. The normal force. This is a new one that you probably haven't heard before. The normal force is a force of a surface exhibits on an object. So you come into contact with this force all the time. It's in everyday life. If you're sitting down right now, a normal force is what's keeping you on your chair. The normal force is the force a surface exhibits on an object. And so you can see here, this table that's holding this box up exhibits a force upwards, and it's what keeps the box on the table. You may have never thought about that before, but obviously that box stays on the table somehow. Gravity's pushing down, so somebody's got to push back up, right? Something's got to keep that object on the table. Well, the table pushes back up. And you can know that. Whoops. So it's got to push back up. And so we call it the normal force. Normal does not stand for like ordinary. That's not what normal means. Normal is an older version. It's a fancier version of saying perpendicular. So the normal force is always perpendicular to the surface. Later, we're going to deal with some slopes, in which case you can see over here, if we have a slope, the normal force does not push up. It pushes at an angle. It pushes perpendicular to the surface. It's always perpendicular to the surface. And there's a video there. I'm not remembering exactly what this video is on, but I think they're all Mythbusters. And so if you want to watch that video, enjoy. Friction. All right, so we all probably know what friction is. Friction is a force that opposes motion. If you're trying to drive your car to the right, friction is going to slow your car down to the left, right? If you're trying to push a couch to the left, friction is going to push back to the right. It's always opposing your motion. It always wants to cause things to stop. Force is always parallel to the surface, so contrary to the normal force. If you can see over here, if we're on a surface like this, and the motion is this way, friction, of course, is pushing this way. It's pushing back to the left. And as you can see, that force is parallel to the surface. The surface is going left and right, and the friction force is going left. Therefore, it's parallel, right? So it's always going to be parallel to the surface. And so even if I have a slope, remember that if a box is sliding down the slope this way, that means friction is going up the slope, right? It's trying to slow you down. It's trying to make you not fall down the slope as fast. It's always parallel to the surface. You can see these parallel lines right here. So friction has a special equation, just like the force of gravity did. Not all forces do, but the force of gravity had its own equation. Frictional force also has a special equation. The equation is there. Force of friction equals mu times normal force. So we've already seen this before. The normal force is what we just talked about. That's the normal force. This is something different. It's called mu. It's spelled M-U. It's a Greek letter. It sounds just like the Pokemon Mew, yes. It's the coefficient of friction is what it's called. All that is it's a relationship between surfaces. If you have two surfaces that are really slick, you're going to have a smaller coefficient of friction. If you have two surfaces that are really at a lot of friction, then you're going to have a high coefficient of friction. It's just the relationship between the two. If you have rubber on wood, that has a lot of friction, so you're going to get a high coefficient. If you have rubber on ice, though, that does not have a lot of friction. That's why you slide whenever you have shoes on ice. And so you're going to have a very low coefficient of friction. There's two types. You need to conceptually know these, although we won't get into the math of the different two because it gets a little confusing. That's more of an AP thing, but we will talk about conceptually. Kinetic friction is while an object is in motion, and static friction is while an object is at rest. And so there's another brain break video there. It's just, I think it's about the phone book friction. If you haven't heard of the myth, you can take two phone books and you can interlace the pages one by one. And if you get all the way through the phone book one by one, it becomes almost impossible to pull apart the phone books without just ripping the phone books. In fact, I believe when they do the experiment, they end up having to get two tanks to pull it apart, and it just completely obliterates the phone books. In fact, you can't actually pull the phone books apart when they're interlaced like that. You just have to straight up rip it. And so that's just how powerful friction can be. Again, the videos, not necessarily take notes over them. They're just there for fun because I think Mythbusters is more interesting than notes sometimes. So take a brain break. Air resistance. So air resistance, as you can see, has the same notation as friction. And that's on purpose. Air resistance is a type of friction. Okay. You may also see F air, that like in this picture here. That's fine too. If you want to label it F air, that's fine. That's more than okay. But normally I will label it F of F because air resistance is just a special kind of friction. Although it doesn't have the same formula. And so note that you can't use that formula with air resistance. So air resistance is the force of air on an object that's in free fall. The last couple units, we've kind of ignored air resistance, like when we did projectiles. We didn't talk about it. We ignored air resistance. And we're still going to, for the most part, ignore air resistance in this unit, except if I mention air resistance, you need to assume it exists. If I never mention air resistance, disregard it. Don't worry about it, okay? Only if I mention air resistance in a problem will you need to talk about it. So air resistance is a result of friction. It pushes up on an object. So if we're always falling down, therefore, if there's air resistance, it's always going to push up. At least in our case, we're only going to deal with up and down air resistance. We're not going to deal with like cars air resistance or anything like that. The main note with air resistance is that when an object reaches something called equilibrium, which we'll talk about later, further on, equilibrium is when the forces are the same. Okay? So it means that as you fall, you're going to be pulled down with some sort of force, right? Downwards. But air resistance is always going to push you back. But of course, you're going to keep accelerating, right? Unfortunately for you, fortunately for you, as you free fall, air resistance actually increases with velocity. So the faster your velocity is, the more air resistance you get. Up into a point where the force downwards, your weight, matches the air resistance. It increases so much they end up being the same. And once the forces are equal, we get zero acceleration. We call that equilibrium. We'll talk about that more. The main thing there is that whenever we reach equilibrium, we get something called terminal velocity. Once the forces are the same up and down, you're not accelerating anymore. You have reached your maximum velocity possible. And so I think this video actually references a penny drop. There's a myth that if you drop a penny off a building, you could kill somebody. That's actually not true, because pennies, when you drop them, they have a terminal velocity. At some point when they fall, they're going to reach a maximum velocity they can get before air resistance is just too much and causes them to stop accelerating. It's still going to hurt a lot. It's not pleasant to get a penny thrown at you, but it's not going to kill you because it's not going to be able to speed up all the way. There's a terminal velocity there. There are better videos on YouTube that talk about this term, more interesting videos. That might be something worth Googling on YouTube just to understand the term terminal velocity. Tension. Tension is the force of a rope on a string on an object. So just anytime you attach a string or rope to an object, there's a tension force. It's the only force that isn't represented by F, so we use a T instead for tension, instead of an F. This is for complicated reasons. I won't get into it in this course. It's not important, really. But it just happens that in general, we notate tension by a T instead of an F. And so that's just good to know. And the main thing about tension is that tension is the same throughout a rope. Right now, it's not super important. We're not going to talk about it too much today. But once we actually do some tension problems, this is going to be super important to know that tension is the same throughout the rope. Spring force. So obviously springs produce forces. And they have a special equation. So of course, we've discussed that not all forces have their own equations. Spring force does. The force of a spring is equal to negative kx. So what are those things? K is a spring constant. It's basically just how springy is the spring. How much does it pull? Have you ever had like one of those thick metal springs that like you basically can't move yourself? Those are going to have a huge K constant, okay? They are very, very stiff, and so you get a very, very big spring constant. But if you get like a slinky, slinkies don't have a big, it's pretty easy to pull apart a slinky. I mean, they're going to go back together, right? But they're pretty easy to pull apart. So they have a very low spring constant. So that's your K. And that's always something it's either given or it's something you're solving for, okay? So don't worry about like, is there an equation for K or something like that? No, there's not an equation for K. It's just something you're given or you solve for. Also X. So X is not position necessarily, but it's how much you've stretched or compressed the spring. And so if, some spring is like this, and then you stretch it like 2 meters, right? Then that means X is 2 meters. You've stretched the spring 2 meters more than it is naturally, and so it's 2 meters. You can also take the same spring and compress it, right? You could push it in on itself. You could push it in 1 meter, in which case you have an X of 1. But in this case, it's -1, right? Since we went to the left. So the direction on X does matter. Make sure you have that direction in there. And you can see an example here. Why does direction matter? Well, if I compress the spring, so if I have a delta X that is negative, right? That means I have a positive force. And you can see it in the equation up here. We have a negative kx. If you have a negative here, that means we have two negatives that cancel out. And so we get a positive force. And so when you compress the spring to the left, the force is to the right. And that should make sense. If I push on the spring to the left, the spring is going to want to go back right. It's going to have a force that restores it back to the right. And so we're going to have a positive force. And same idea here. If we stretch the spring to the right, and so we have a positive x, you can see in that equation, we're going to get a negative number. And that should make sense because if we stretch the spring to the right, the force is going to be wanting to be back left. It's going to pull to the left, which is negative. Applied force. So we've basically covered all the main forces. And so obviously other forces exist out there. We haven't covered every single main force. We're going to get to some more on like electricity. We'll study that later in the year. That's actually a more interesting and more fun unit if we can do labs. We'll see what happens. But applied force is any other force not specified. Like if I just push a car, no one's going to give Mr. Wilson a special force named after him just so his force has a special name, right? And so there's not like there's a force of W for Mr. Wilson when he pushes on a car. We don't do that. Instead, we just call it, it's an applied force. It's a general applied force anytime an object's apply force on each other. And so, and whenever we do that, we're just going to number them. And so if Mr. Wilson pushes on the car, we'll call it F1. And if somebody else pushes the other way on the car, we'll call that F2. We're just giving them numbers because we don't really have special names for them. And so we just assign them whatever you want. If you want to, in a problem, it's probably actually better, say, it says the man pushes on a car, so put F of M, and then a woman pushes on a car, put F of W. That way, whenever you're solving your problem, you know that this belongs to the man, this belongs to the woman. The main idea here is that for whatever reason, students get so caught up in taking notes that they don't understand what I mean by applied force. I'm just saying it's just whatever other force. And so we don't have special names for them, so just give them a special name. You can name them whatever you want. All the subscript is down here is a name, and so you can name whatever you want. Most of the time, we just number them, and that's what I normally do. I just number my forces. All right, finally we get to the best part. Newton's second law. Sir Isaac Newton created 3 laws in physics. You've probably heard them all before. At least you've heard the first and third law, most likely. We're actually not going to cover those ones today. We will cover them more as we go on. They'll become more important whenever we do some conceptual stuff. But for the most part, they're not super important in any of the math that we're going to do. And we're going to try to get most of the math out of the way as soon as possible, because it's the hardest part. You need the most time to chew it. The conceptuals of this unit are not too bad. We don't have any crazy graphs or anything. Okay, so the second law says F net equals ma. The second law is actually an equation. F net stands for the sum of all the forces. And so obviously any force, or any mass can have a number of forces on it. If a car is accelerating, that means 1, gravity is working on it, because gravity is always working. But obviously that car is not going through the street, so that means the street is applying a force to keep the car on the street. So that's a normal force, right? The car is on the surface. Let me draw the car right here, just so you can see it. Here's my car. Gravity's pulling down, but so that the car doesn't go through the earth, we also need to have a normal force up. And if it's accelerating, it's got to have some sort of applied force by the wheels forward, right? So we call the net force the sum of all the forces. If we want to figure out the acceleration of this car, we got to add all these forces together to figure it out, because there's multiple forces here. So if we want to figure out what the acceleration is, we need to add all the forces together. That's all net means. It means sum. We actually don't need to do the math today. We're going to cover the math next time. The main idea here, though, is that if the forces are balanced, and by balanced I mean this equals this, and there's also maybe some frictional force backwards that balances this force, right? If all the forces are balanced, that means F net is 0, right? If all the forces are balanced, these 2 vectors cancel out, so there's 0. And then also these 2 vectors cancel out, so there's 0. And so overall, the sum of the forces is 0. If all the forces are balanced, F net equals 0. And so if this equals 0, obviously mass can never be 0. You can't have a massless object. So that must mean A equals 0. If the sum of the forces are all balanced, A equals 0, and we call this equilibrium. So that's what we were talking about back in the free fall. In free fall, when we had the force upwards was equaling that force downwards. When our air resistance was equal to our gravitational force, we had 0 acceleration. We stopped accelerating, which means our velocity stopped changing. And so we reached a max velocity, and so we call it terminal velocity. When the forces are balanced, A equals 0, and then we have equilibrium. This is super important. There's going to be multiple questions like this, both math questions and conceptual questions. You need to know equilibrium. You need to know that means A equals 0. You need to know that means F net is 0. This is a foundation for our unit as a whole. In this video, it doesn't actually have too much to do with equilibrium, but it has to do with the equation a little bit. It's just a fun video to watch. So there you go. Let's get into the free body diagrams. This is the meat of today. This is what your homework is going to be over. So I've been drawing these in and out, and they've been on some of the slides. A free body diagram is a system of us helping add force vectors. It's basically a picture. We're going to be drawing pictures today. But there's a specific system to be drawing pictures. Okay. Here's an example. If we have a book on a table, our free body diagram would look like this. Isn't labeled enough. I actually need to fill in a couple things that I didn't feel like putting in the PowerPoint slide. But it should look something like that. And then we might do this at the end. It's going to look something like this. It's just a picture. Okay, let me show you the instructions on how to do it. You start off with a box. Obviously, whenever we have problems, it might say an elephant is like this. We don't have enough time for you to sit and draw an elephant. I don't care if you're in art, 5 or art 12 or whatever. I don't care how good at art you are. We're not going to sit time for you to go through all the steps and draw a really, really nice elephant. Draw a box. Simplify it. We're just drawing a mass. We're just drawing a box. If you really want a circle because your object is more circular, draw a circle. That's fine. But just draw a simple shape. Then, and so let's start with that. I'm going to do it on the side here as we go. So let's say my example here is we have a couch pushed across the floor. Sure. Okay. So then once we have our box, so this is my couch right here. This is my couch. It's very nice looking. We need to draw a coordinate system. This may seem obvious. We're always going to have y up and x to the right, right? But we need to draw a coordinate system in here every time. Because guess what? Our coordinate system will not always look like this. Our coordinate system will change. You are not used to having a changed coordinate system. You're not used to have one that doesn't look like this. That's okay. We will cover it when we get there. It's really not too bad. But just note that it won't always be like that. And so we need to establish a coordinate system before we do any of the other stuff. Thirdly, we're going to draw force vectors. So what force applies to this object? In order, the first one you should always think about is, okay, is gravity existent? Are we on a planet? Yes, we're probably on Earth. I didn't say it specifically in the problem, but we can safely assume we are on Earth. And so and it's also pushed across the floor, which means that something's pulling it down, and so we have to have gravity, right? And so there's some force of gravity down. Okay. After you get gravity, the second thing you should think about is, are there any forces, or is there anything touching my box? Is there anything touching the box? Well, there's actually two things touching the box, right? First thing is the floor. The floor touches the box. So if we're on a floor, that means we're on a surface. Well, that means we have a normal force, right? This box is not going through the floor. This box is not just like phasing through the floor like some, glitch in a game or something like that. It's not, this is real life. It's not just going to phase through the floor. We have to have a force that opposes the box from going through the floor, so we have a normal force. Okay. Also, if we're on a floor, if we're on a surface, we can assume there's friction. And so if we're being pushed to the right, that means there must be a frictional force backwards. Now, you can draw all the forces from the center of your object. I like to put friction at the bottom of my box because that's where the friction is applied, right? Frictional force is applied to the bottom of the surface. So I'm going to draw my force there. Some diagrams will have you put it through the center, like this. But I don't really care for that. I think I like it where it's applied. So I'm going to erase this a little bit. I like to put it where the force is actually applied. And the force is actually applied to the bottom. And I should emphasize, my normal force is starting here too, right? The normal force is applied at the bottom. And so that normal force is coming from the bottom as well. But you might see diagrams where they all put them in the center. That's fine. Also, we're being pushed. So that means some person or some human or animal or whatever is pushing the couch. And so we have some sort of force that way. So a couple notes here. All forces must be going outwards. Yes, I understand pushing means that the force is going into the box like that, right? I don't really care. All forces come out of the box. All forces start somewhere at the box, whether it's on the side or in the middle. Whoops. Whether it's inside or in the middle, and they come out. And so when you draw this, you draw FG down, you draw normal up, we draw friction coming out, and we also draw the push force coming out. We'll label F1. And don't forget your coordinate system. And also need to label them. I already did that. You label them with their names. So this is F1, this is Fn, this is F of F, this is F of G. Great. And then we're going to go ahead and get into the habit of just writing this every time. F net equals MA. I want you to do this in the homework too. Every time. We're not going to use this today. We're going to use this next time. But every time I want you to write it. F net equals MA. F net equals MA. I want you to know this thing by heart. I want you to tattoo this on your arm. This is the fundamental equation of all of physics. This is it. This is the creme de la creme. This is it. You need to know this equation. F equals MA. So let's do a couple of examples before we stop going. If it will go. All right. Crate of books is on a slope. A kid is pulling the crate up the slope with a rope, and another kid is pushing the crate up the slope. Draw the free body diagram. This is a complicated one. I did this on purpose so you can see everything. So we're on a slope. So I'm going to tilt my iPad so I can draw a box sideways, right? Our box is on a slope, so it's sideways. I will say, if you're on a slope, if you want to, you don't have to. If you're on a slope, you can go ahead and draw the slope in here. That's fine too. That is totally allowed on a free body diagram. You can draw the surface you're on. All right, so first thing, after we draw our box, draw our coordinate system. Secondly, draw our forces. What forces are applied? Well, gravity is going to be applied. What other forces applied? Are we touching a surface? Yeah, we're touching a surface. So that means we have a normal force coming out of the center. And we have a frictional force. And if it's going up the slope, right? So we have, if it's going up the slope, that means the frictional force is going down the slope. Sorry, I had to read that for a second. It took me a second to register. If we're going up the slope, that means frictional force is down the slope. What other forces are applied? Well, we have a rope being pulled on the box. So we have some sort of tension force going up the slope. We also have another kid pushing the crate up the slope. So that means we have another force coming out of the center. So we can just draw another one. That's an applied force. And I think that's it, right? We covered the kid pulling. That's a tension force with the rope. And then we covered another kid pushing the crate. So that's the applied force. We covered the surface, which is normal and friction. And we have gravity. So that looks like our free body diagram. So once we do all that, we write F net equals MA. There we go. Here's another one. Rocket blasts off a launch pad. I'll let you do this yourself. Pause the video. Do it real quick. Okay. So for this one, it should be pretty simple. We have a box. Well, and we draw a coordinate system. I always forget to do that. We got to do that too. I got to remember to do that as well. We have F of G down, right? We definitely have gravity because we're on a launch pad on Earth. If we're launching off, though, that means we have some sort of applied force up. We're launching off, so that means the normal force isn't really at play here anymore. We're launching up so that we have some sort of F1. Now, this is my last note. If the forces are unbalanced, if we're blasting off, you need to make sure you make this force bigger than the other force. That way, it looks like, hey, this is pulling more than that. This force is pulling more than this force. Therefore, it is accelerating upwards. That's part of the whole idea of a free body diagram. You want to get the idea of where is this thing moving? Where is this thing accelerating? This describes it perfectly because we have a bigger force up than we do down. Therefore, I know we're accelerating up. And so I kind of have expectations of what kind of values I'm going to get. I'm going to get a positive A whenever I solve this problem if I had numbers. Whoops. I can discard them. Whoops, hold on. 1 second. Let me get back in here. Okay, so in physical classroom, we're going to be doing whiteboarding today so we can get some practice doing free body diagrams. We're going to be going to this classroom or this website, Physics Classroom. I'm going to post it on the board. They'll do whiteboards over all the problems. We'll go through them all. This is actually good help. If you want to do this, this will give you feedback immediately on whether you're doing your free body diagrams correctly. They label them a little differently than I do. And they also put all the forces at the center. If you label like them, that's totally fine. The way they do the free body diagrams is 100% acceptable in my course. So you can follow it and be okay. I don't mind it at all. I would suggest using our notation for like, they, instead of F of G, they put F of gravity. That's just longer. Just put F of G. I suggest using my notation instead of theirs on that. But it doesn't really matter. I think they also might use F of T instead of T for tension. If you want to use F of T, you can, but I suggest using my notation. Besides that, you can totally use this. It's good practice, and that's why we're doing it in class as well. So I wanted to offer that to you. It's not a grade, but I wanted to offer you some of the stuff we're doing in class to you as well. And then also go ahead and start the homework. The homework is just doing a bunch of free body diagrams. Once you go into a rhythm of it, it shouldn't be too hard because it's just drawing pictures. You're doing the same thing each time. You're just drawing boxes and you're drawing arrows. It should be easy enough. There's not too much thinking involved because there's no like actual calculations. There's no math today, which is nice. We'll get into the math next time. All right. With that, good luck. Ask me questions. Come to tutorials. I always have tutorials Tuesdays and Thursdays after school, but I'm not going to get on if you guys don't ask me to. But I have gone on for those who do. Please ask me if you want to get on, and I will be online for you. With that, thank you. Have a good day.